Dear students, welcome to our first lecture on module on support vector machines. In our videos on mathematical foundations, we learned so many concepts around bases, spans, transformations, projections, and so on. But now the question arises how we will put these concepts to some real world applications. And the first problem that comes to mind in the context of machine learning is the problem of classification. Now, with all the concepts that we have learned as part of maths of ML, the approach that can put it to justice would be support vector machines, which is really tricky to learn if you look into the involved mathematics. But with the background that we have built, it should be like an easy concept to cover. So what these support vector machines are, what this classification problem is, let us start looking into that. We have learned that we will typically deal with data sets which is arranged in some matrix form, and the dimensions of this matrix would be given by n cross d, where d is the dimensions or features associated with that particular data. For example, if we are talking about xi vector, which talks about one specific instance of observation, let us say associated with the climate at particular place I. So in that case, we would say that we will measure certain features, that what is the value of temperature, what is the value of humidity, what is the precipitation, what is the wind speed in various directions, U wind, V wind, and so on. So basically for any given city, we can characterize the climate based on these variables, or state of the atmosphere. I should not use the word climate, but state of the atmosphere using these 7 variables. Similarly, you can have n different cities and collect these features, temperature, humidity, precipitation, and so on. And this can finally be wrapped into a matrix form x of n cross d. Now, what we are looking at is that if we treat all these values of climate at day 1, day 2, up to day n, and we are trying to look into the basic clustering problem. So let us say that based on the atmospheric conditions, we want to classify that day could be pleasant or it could be uncomfortable. So we are coming up with some user rating, pleasant and uncomfortable, and we know that certain combination of temperature, humidity would result in a comfortable versus a non-comfortable day. Again, we are taking a very simple example where we know that outcome could be binary. So we are dealing with the problem of a binary classifier. So formally stating, the problem begins given the certain value of features encoded in xi, we have the label associated with yi, and these yi's are basically either pleasant or uncomfortable, and we want to train a classifier such that whenever we give some x input and add some bias, we should get an output as +1 or -1, where +1 is the state associated with condition being pleasant and -1 is the state associated of for the condition being non-pleasant or uncomfortable. Now you can change this temperature with any kind of variables of your choice. So let us say you are looking into a classification problem of a healthy person versus an unhealthy person. So basically there you would look into certain medical attributes as a feature, and your yi's would be healthy or non-healthy, or person is positive for particular disease or he or she is not positive for particular disease. Now basically if you look at this form again, wx plus b, this also looks like the regression problem. Remember that when we were talking about regression, our idea was same. Give us some x, we will multiply them with some weights, add a bias, and we will try to come up with the predictions. But in case of classification, we would be making a discrete decision. That is, either it's a pleasant or it is uncomfortable. So while regression is also a machine learning problem, but it is typically solved in continuum. Whereas classification is a problem that we will solve in the discrete world, where we know that outcomes are going to be one of many finite cases. Now stating this thing formally, we are looking for a function f that will take xi is having d features, so it will take a vector in d dimensions and give us output in a real space. And we say that this function can be written as w1x plus b. Now we will try to learn about that how to build a classifier all the way from scratch, what goes inside one of the most sophisticated classifiers, what we call as support vector machines, and discuss what are the various terminologies associated with it. Now, whenever we are talking about classifier, what we are trying to do is that let us say that we have two samples. One is classified as negative and another is classified as positive. We are essentially looking for a decision or a decision boundary such that points that lie on one side of this decision boundary, they are all classified as negative, and points that are lying on the other side, they are all classified as positive. Now, if we have many points, let us say we use this orange color to represent all the points that are associated with not so pleasant weather, whereas we have points uh, put down here in black that are associated with some positive or healthy environment or good conditions out there. The question arises where we should put this decision boundary so that our decision boundary is optimal with minimum to no error, so that whenever a new sample comes, we should be able to classify it correctly. For example, let us shift this decision boundary from here to somewhere here. Now you will see that in comparison to the boundary that we had before, which was somewhere here, all the points that will lie in this area would be misclassified, which is of course not good. So in mathematics, the question that we are posing is that what is the optimal location of this decision boundary so that our two classes or multiple classes are well separated. Needless to say, our intuition will say that we should start looking at the boundaries if we have to locate such a point. So boundary of one such point which is classified as negative is here. Another point which is classified as positive is here. And we want this margin to be maximal separated from orange as well as from this point, which is the first case that we are finding towards going in the positive uh, classification region or positive area. So support vector machines give us a way to identify these optimal boundaries mathematically. Also, when we were talking about the basics of machine learning from mathematical side, we learned the concept of vector subspace. And we learned that vector subspace should have 0 as its element. However, what would happen if 0 is not contained in vector subspace? That is, let us say our 0 is located somewhere here and there is a line segment. If we are talking about a two-dimensional space, so this is R square, we say that this particular line would not classify to be a vector subspace of R square because origin is not contained here. So we call these special elements falling in vector spaces as hyperplanes or manifolds. So basically, to define the characteristics of such hyperplanes or manifolds, in addition to the vectors that are located along these elements, we also need a term which represents the bias or shift from origin. And when we will deal with the mathematical aspect of support vector machines, we will call such elements that are shifted away from the origin as hyperplanes, and we will try to pose the SVM as the problem of hyperplane positioning. Thank you.